Okay, so let's take a look at this sample problem. So it says a Gaussian surface in the form of a cylinder of radius r immersed in a uniform E view. Uniform E view. So with the cylinder axis parallel to the field, what is the flux phi of the electric field through this closed surface? So this is a cylinder, 圆柱体. And yeah, so this is the axis because we have two circles in parallel, and then we connect all the other point together. So this is a cylinder, and yeah, and so this is the axis which is parallel to the line connecting the center of the two circles. So this is the axis of the cylinder, which is parallel to the field. So now we can see the field is pointing to the right side, and what is the flux through this closed surface. Okay, so so we need to calculate the phi, which is the closed surface integral of E over the area of this cylinder. So let's call this part part A. So this circle, we call it A. We call it A. And the right-hand side circle, we call it C. And the middle part, we call it B. So this integral can be separated into three different integrals. Yeah. Because integration is linear operation. So for this one, we calculate the whole cylinder. So we separate into part A, part B, and part C. So nothing special. And yeah, for part, so let's see. So for part A, so we consider E is pointing to the right side, DA is pointing to the left side, because when we consider the vector, yeah, the area vector, it should pointing to the outside and perpendicular to the plane. So so DA for surface A should be pointing to the left side. And in that case, E dot A is a negative number. E dot A is a negative number, and the theta is 180 degrees. So cosine of, so it is like E times A, because E is uniform. E is uniform. So we will consider this area to be A, or actually pi r squared. But it depends how you try to write it. A, and then cosine of 180 degree. This is theta. This is theta. So cosine of 180 degrees is -1. So E times A times cosine 180 degree is negative EA. Okay, so next part is part C. So here, for this surface, when you consider pointing outside, E is pointing to the right side, and DA should also pointing to the right side. So in this case, E times A cosine of 0 degree, which is 1. So we have a theta A. Maybe this one is theta C. So this is a theta A. This is theta C is 0 degree. So we have E times A, because cosine 0 degree is 1. Okay, so the remaining part is part B. So let's consider this side surface of the cylinder. And also the E field pointing to the right side. However, the dA should be all the way perpendicular to the surface. Although it is not a plane, but this line is not difficult to find because you can feel like, oh, this is the center of this part, and then you try to connect the center point to this point and then pointing outward. So it will be perpendicular to the surface. And suppose it is this point, then it is somehow it's difficult to draw a 3D plane. But actually, you can find dA should be all the way perpendicular to the E field. So here we will have something like E times A cosine of 90 degrees, something like that. Yeah. And this part should be 0. This part should be 0. So we have 0 for this part. So we have phi equals minus EA plus 0 plus EA, which will be nothing but 0. So this is a simple question to demonstrate how to calculate the electric flux or the net flux. So it is nothing special. So any question? If you have any question, so feel free to leave it on the comment or yeah. Okay, so I try to go forward to the next sample problem. So it says a uniform electric field given by E equals 3xi plus 4j. So x is I is the unit vector in x-axis, j is the unit vector in y-axis. Here's the Gaussian cube as shown in figure. E is in Newton per Coulomb, and x is in meter. So what is the electric flux through the y surface, left surface, and top surface? So let us calculate the electric flux through the right surface, y space first. Okay, so here, let's consider this E dot dA over the right surface. So we use a small r to represent right. Okay, so in this case, we should have E dot dA. So for the right surface here, so dA should be pointing to the right side, as it is perpendicular to the surface and also pointing to the outside. So it should pointing to the right side, which means it should be like this is x-axis, so it is I hat dx, something like this. Okay, so we have E dot dA. E dot dA will be 3xi plus 4j dot I hat dx. So if you still remember, I have mentioned that the unit vector, if I dot I will be 1, I dot j or j dot I will be 0. So it dot itself when the unit vector in the Cartesian coordinate, if they're dotting to itself, then it will be 1. If they dot with other unit vector, then it will be 0. So it will be something like 3x I dot I will be 3x dx. And then j dot I will be 0. So we only have a 3x dx left. So we will have integration of 3x dx. And then actually we let me see. No, so it should not be dx. It should not be dx. It should be dA. It should be dA. should be dA, dA here, dA here, dA here. Yeah, should be something like no, we don't have the integration sign here, so should be dA. It should be dA because this is a area vector. So this amplitude should be an area. Okay, and of course we need to integrating it over this area, but it is actually a constant because here we have a fixed x to be 3. So here it is x equals 3 meter, which means that it should be something like R 9 because it is 3 times 3 dA. And this is like integrating a constant over a variable. So it is nothing but equals 9 times this area. This area is actually 2 meter for each side. This is a cube with the length of 2 meter because this is 3, this is 1. So we have 2 for each side. So it is like 2 square is the area. So this is looking quite strange, but actually is somehow like integrating 4 over dx from 0 to 3, then it will be 3 times 4 equals 12, something like that. So if you're just integrating a constant, then it's nothing but a multiplication. So it's the case like this, integrating line over this area. So this area is 4, so 9 times 4, which is 36. N Newton meter square over Coulomb. So this is the answer to part A. Okay. Oh. Okay. So for part B, we try to calculate the plus or the left surface. Okay, so it is nothing special, but here we have dA pointing to the left side. So it should be like negative I hat dA. So here we will have E dot dA to be 3x I hat plus 4j, and then dot negative I hat dA. So 3x and then I hat dot I hat will be 1. So we have a negative 3x dA. And then j hat dot I hat will be 0. So we only have this term. And of course, here we have x equals 1 meter. So it will be evaluated at x equals 1 meter. So it will be negative 3 dA. So here, integration of E dot dA over the surface of the left side. So we have a integration of minus 3 dA. So in this case, we have a minus 3 times 2 square, similarly. And we have a negative 12 n times meter square over Coulomb. Okay, so this is the answer to the question B. And for part C, so we would like to calculate it over the top surface. So this is y-axis. So dA will be pointing to the right axis, which is j hat, so j hat times dA, something like this. Okay, so now we have a E dot dA to be 3x I hat plus 4j hat, dot it with j hat dA. So here, I hat dot j hat will be 0, j hat dot j hat will be 1. So we have 4 dA. No, we don't have vector sign here. So it is a 4 dA. And in that case, integration of E dot dA over the top surface will be integration of T 4 dA, which will be 4 times 2 square, which is 16 Newton meter square per Coulomb. Okay. Okay. Any questions? Okay. So we come to the main part of this chapter, which is the Gauss Law, So for the Gauss Law, it says it relates the net flux of the electric field through a closed surface, a Gaussian surface, to the net charge that is enclosed by the surface. It tells us that epsilon naught times the net flux equals to the Q enclosed by that Gaussian surface. So it is very simple. It looks very simple. It's just like the Newton's second law of motion, F equals ma, something like that. Then you'll be able to learn it in high school. And actually, a more complicated way for the Gauss law will be like that. Oh, here comes the integration, which is not good looking, but actually it will be more useful. It is somehow like for F equals ma, when you use it, it will be something like, you only have a constant acceleration, then you'll be able to calculate. If the acceleration is not a constant, then probably you may not be able to solve those kind of a question in high school level without the calculus. So in bachelor study, probably if you really need to use the Newton's second law of motion, it will be something like F equals m times the second derivative of x with respect to time. Then it will be more useful. Yeah. So this is something like that, but here we don't use the derivative. Rather than that, we use the surface integral like this. And of course, in chapter 32, I will tell you the differential form of the Maxwell equation, of course, including the Gauss law. Then we will have the differential form, something like this one. The divergence of E is the charge density over this epsilon naught. I will tell you how to derive this one from this one using some mathematics. But let's talk about it later. Okay, so for the Gauss law itself, it is something like this is the net flux. This is a constant epsilon naught, which is 8.85 times 10 to the minus 12 with the SI unit, and this is a Q enclosed. So let's see how it demonstrates on the right hand side figures. So for the first one, we have S1. S1 is the orange closed surface. So although it is like a 2D graph, but try to imagine it to be 3D. So it is a closed surface rather than a plane. It's not a plane at all. So it is a 3D surface. So, and then here we have a positive charge inside this S1. So it tells you that the net flux, the flat net flux which is the E field, integrating the E field over this surface, times the epsilon naught, which is a constant, will be equal to this charge, And it doesn't really matter where is this charge. For example, if the surface is like this, and let me copy this, and then let me place here. Yeah. So suppose we have a positive Q here, or if we have a positive Q here, or if these two figure is independent. So these two shape is actually these two Gaussian surface are actually the same, but the position of the enclosed charge are different. However, Gauss law tells us that the surface integral, which means the net flux of these two cases will be actually the same. Although if you find this point and this point, the E field might be different, but the integration, the first surface integration is like the summation, the addition. So we add all the E dot dA together. It turns out that the answer will be the same, even though the E field at different point, at every point might be different. So it tells you that if we have a positive charge here, then we will have a net flux to be positive, which means the net flux will be pointing outward. And for S2, if we have a negative charge inside this Gaussian surface, then the net flux will be pointing inside. So you can see many arrows pointing into this Gaussian surface at S2. And for S3, S3 is somewhere here, which means it doesn't have any charge inside this Gaussian surface. But as you can see, some of the E field are pointing into this S3, and some of the E field electric field line are pointing outward from it. And the Gauss law tells you that we don't have any charge inside this S3, so the net flux will be zero. Because there is no Q enclosed. Or the charge are outside of this S3. So this Q enclosed for S3 will be zero. And this is a constant, so only this integration could be zero. So the integration for S3, the surface integral for S3 will be zero. And for S4 is the big one. Which is like an egg. So S4 totally enclosed this plus and negative charge. Of course, we assume this charge have the same magnitude. So it turns out that the net charge enclosed by S4 will be zero. So in that case, according to the Gauss law, it tells you that the net flux for S4 will also be zero. So we have a phi1 to be positive, phi2 to be negative, phi3 and phi4 both equals to zero. So this is general introduction to the Gauss law. It might be a bit difficult. If you have if you could understand, just leave a comment and I'll try to explain it again. Okay, so next, it says the Gauss law is compatible to the Coulomb's law. So it could actually we could actually derive the Coulomb's law from the Gauss law. Yeah, so let's see how we can apply the Gauss law for a charge. So here we have a charge Q. Can be either positive or negative. It doesn't really matter. And then we define a Gaussian surface. So actually, the most difficult part to apply the Gauss law is how we could define a suitable Gaussian surface. But of course, through the lecture slides, it automatically tells you that how to define the Gaussian surface. And if you try to revise the selective problem, then you will find different problem may try to define the Gaussian surface in a different way. But yeah, so it is somehow like there will be some tricky part to find a suitable Gaussian surface. But yeah, actually you can try to follow the logic behind that. So here we have a positive charge. We try to define a sphere. Enclosing this charge, and the center of this sphere is actually at this charge. So we try to apply the Gauss law here, and for this Gaussian surface, so we have epsilon naught times this surface integral equals Q enclosed. And according to our knowledge, we know that the E should be pointing outward if it is a positive charge. If it is negative charge, it will be yes. So now we just assume that Q is a positive charge and E is pointing outward, which will be perpendicular to dA, because it's just a sphere. So pointing to the outside is actually perpendicular to the surface. So E dot dA is nothing but EDA, because cosine 0 degree is 1. So we have simplified this term like this. And next, we will also consider that because it is a sphere, so the distance from the surface of every point will be actually the same to the center. So we will consider E is a constant over the whole Gaussian surface, which means that we are just integrating a constant over a surface, which means we can just factor it out, and then we calculate the surface area, and then we multiply them together, then it is done. So we just factor out E, because E is a constant to the area. And then, so we know that the surface area of a sphere is 4 pi r square. I suppose you have learned it in high school. If you don't, you can just remember it now. And so this is the surface area of a sphere, 4 pi r square. So we just subtracting this term into here. So we have epsilon naught E times 4 pi r square equals Q enclosed. Okay, so it is all done. The remaining part is to just move this term to the right side, and it's done. So we have E equals 1 over 4 pi epsilon naught times Q enclosed r square. So we have 4 pi epsilon naught will be like this. Usually we use it as K and Q over r square. So this is what we have found in chapter 22 about the E field from a positive charge. And actually, it should compatible with also the F equals QE. So it is the Coulomb's law. So actually, this is the Coulomb's law. So actually, the Gauss law is compatible with the Coulomb's law. Okay, next we would like to see another sample problem. So here in cross section, a plastic spherical shell, uniform charge Q equals -16e and radius r equals 10 centimeter. A particle with charge Q equals plus 5e is at the center. So this small q is plus 5e. And then the capital Q is negative 16e. Okay, like this. So it's a plastic spheres. Plastic means it is isolator. Yeah, which means the charge on it is not free to move. Okay, so what is the electric field at point P at radial distance? R1 equals 6 centimeter. R1 equals 6 centimeter because the capital R here, it is this is capital R equals 10 centimeter. So point 1 here is 6 centimeter from the center. Okay, so we consider a Gaussian surface here, which is also a sphere with the center at the charge. So okay, so let us apply Gauss law for this Gaussian surface. So it is Q in charge, which is small q. So here, similarly, because it is all the way symmetric, so E dot dA is nothing but EdA, and then E is a constant, so we can have E epsilon naught E times 4 pi. This is R1. This is R1, so we have R1 squared equals Q. Okay, so we can have E equals 1 over 4 pi epsilon naught times Q is actually plus 5e, which is over R1 squared. So we can substitute the number. This is 8.99 times 10 to the 9th power times 5e, 5 times 1.6 times 10 to minus 19 elementary charge. So over 0.06, because it is 6 centimeters, so you should convert it to 0.06 meter. So this is nothing but 2 times 10 to minus 6 Newton per Coulomb, or you can write it as 2 micronewton per Coulomb. So micron is 10 to minus 6. Actually, for some of what we call is scientific prefix, you probably need to remember some. So for mega, giga, mega, you probably will be very familiar with that. This is giga, and mega, kilo. I suppose you should be very familiar with it because when you use your computer, you should face this scientific prefix very frequently. And for 10 to minus third, you also know milli, because you know millimeter or milliliter. And then 10 to minus 6 will be micro. 10 to minus 9 will be nano. And then 10 to minus 12 will be pico. 10 to minus 15 will be femto. Actually, I suppose you probably need to remember this. Yeah. Because for some of the question, it may occur. Yeah, it may occur. You probably need to remember it. Okay, so next we talk about part B. So it asks what is the electric field at point P2, which is outside the radial distance, outside this sphere at the radial distance R2. This is R2. So here we consider the Gaussian surface, of course, at this point. This is the P2. So here we consider this Gaussian surface when we apply the Gauss law. Equals Q enclosed. Q enclosed here includes small q and capital Q. So we have Q plus small q, capital Q plus small q. Okay, so similarly, for the left-hand side, we have epsilon naught E times 4 pi R2 square. And then for the right side, capital Q is minus 16E plus, this is 5E. So it is minus 11E. Okay, so we can have E at this point at P2 will be 1 over 4 pi epsilon naught over times minus 11E over R2 square. Okay, so let us subtract the substitute the number into it. So we have 8.99 times 10 to the 9th power times minus 11 times 1.6 times 10 to minus 19 all over R2 square, which is a 0.12 square. So this is nothing but minus 1.1 times 10 to minus 6 Newton per Coulomb, or you can write it as minus 1.1 micro Newton per Coulomb. So in the quiz or exam, you just include one is enough. You don't need to write both. Actually, if we will try to draw a figure like this is the distance from the center to the point we concern, and then this is the E field. It will be something like this. So this is K times 5E over R squared up to this is 10 centimeter, and then it will flip to here, and then we will have this is K times minus 11E over R squared. If you really like to draw the curve out, it will be something like that, because this is the expression for R to be larger than 10 centimeter, and this is the expression for the R to be less than 10 centimeter. So if you try to plot it out, it will be something like that. Okay. So next, we consider another sample problem. Okay. So here, it is a sample problem we just faced. It asks you, what is the net charge enclosed by this cube? Enclosed by this cube. So just now we already find that phi left, phi right, and also phi top. Also phi top. Yeah. So actually, we still need to find front and back. This is back. Front and back. Why it is 0? Why it is obviously 0? Because for front and back, just say front, dA, this dA will be K hat dot K hat times dA. So if we have K hat here, and then we dot it with this 3xi hat plus 4j hat. So K hat dot I hat will be 0. K hat dot J hat will also be 0. So it is obvious that phi front will be 0, and also phi back. Phi back is dA hat is negative K hat dA. So similarly, phi back will also be 0. So the remaining one is the phi bottom. So for phi bottom will be nothing but BOT and then E dot dA. So for phi bottom, dA will be this dA will be negative J hat dA. So this one dotted with this one will be -4. Will be -4. So E dot dA will be -4 dA. So we have an integration of a -4 dot dA and then bottom. So it is a -4 times Q square, which is a -16 Newton meter square per Coulomb. Okay, so phi total, which is the net thrust of this cube, will be -12 plus 36 plus 16 minus 16 plus 0 plus 0. Yeah, because a cube has a 6 surface, and yeah, it consists of this 6 number, and then we just add them up. We have 24 Newton meter square per Coulomb. Okay, so we can simplify Q enclosed to be phi the net flux over epsilon naught. So which will be something like F equals ma. If you know 2 of them, then you can find the remaining one. So it is 24. Sorry, it should be epsilon. Yeah, it should be the other. It should be something like that. Sorry, it should be something like that. So it be multiplied rather than yeah. Okay, so it should be like 8.85 times 10 to minus 12 times 24. So this one will be 2.1 times 10 to minus 10 Coulomb. Or if you still remember, pico is 10 to minus 12. So we can write it as, or 210 pico Coulomb. So it depends. If you like, then you can use this one. Okay. Okay, so let us have a 10 minutes break.